all of them in a few minutes. So I'm going to copy here the first derivative, which is 3e to 3x minus e to x. Yes, that was correct. Good, I'm just checking. So the original function is here, so that's correct. So now the second derivative will be 9e to 3x minus e to x. Very, the same type of situation, a difficult equation to solve like we just had over there. So it's always defined. So 9e to 3x minus e to x equals 0. I will factor out e to x, and then I have 9e to 2x minus 1 equals 0. Another ugly equation to solve, but let's get it done. And no, this is not a problem for a test. Not for a test. Way too long. It tests endurance. It doesn't test understanding that much. I mean, it does, but okay, you know what I mean. So this can never be 0. 9e to 2x equals 1, which means e to 2x equals 1 over 9, and I have to apply natural log as we did before. So 2x equals natural log of 1 over 9, or x equals natural log 1/9 over 2. And yes, I have to plug this in a graphing calculator. And I'm going to share my screen right now. Okay, where are you guys? I lost you again. Okay, here you are. Good. So I have to determine this number, natural log of 1 divided by 9, close the parenthesis, and divide by 2. Okay, so this is negative 1.1. So x equals approximately negative 1.1. Okay, back to my table. And yes, of course, they had to be so close, right? Negative 1.1. And here it is 0. And I'm going to determine the signs of the second derivative. And where is my second derivative? Here it is. Here's my second derivative. So when I plug in negative 10, we're just going to plug in the calculator just to make sure. So let me share my screen again. I will in y equals, look at that. So, okay, we have 9 e to 3x. And then minus e to x. Okay, and I really don't need the derivative. So I'm going to de-highlight that. So I only want second and table, and I want to plug in negative 10, and then I want to plug in 10 to check the sign. So with negative 10, the second derivative is negative. With positive 10, the second derivative is positive. So I'm coming back here for a second. So we had negative, and then we had positive. Which means here the function opens downward, and here it opens upward, as we expected. Why? It has to open this way if this is a relative minimum. I need to determine this value here, because this is definitely an inflection point. This, comma this, I did not plug it in the function yet. So I'll go back and plug it in the function. So second and table. No, I need to go back here and highlight the function, because I want to plug it in and it will not be there. So negative 1.1, and the value is, of course they have to be so tiny, negative 0.3. Okay, so this is negative 0.3. The inflection point is negative 1.1, the x value, comma, negative 0.3, the y value. the relative minimum is negative 0.55 the x value, negative 0.34 the y value. And finally, that's it. So if you're asking me what are the intervals of increasing for this function, easy. From negative infinity to decreasing first, from negative infinity to negative 0.55. Interval of increasing from negative 0.55 to infinity. The function is increasing. When is the function concave downward? For x between negative infinity and negative 1.1. Where is the function opening upward between negative 1.1 and infinity? Because the second derivative is positive. So this is what we learned from the first, and this is what we learned from the second. And the table has to work well together. All rows. We already checked that these two work well together. All I can check right now is that when the function opens up, if this is a relative max, I'll say, oops, terribly wrong. How can it open up and have a relative max? But it has a relative min, which was expected. Okay. Now I'm ready for any questions you may have. Anything you want. Anything you worked on, anything you had difficulties with, or you want to go back to, anything. Anyone? Okay, 1, 2, 3. Okay, don't worry about the table. We're going to work on the table in the next section again and again and again. So I'd like to show other types of problems from 3.2. So 3.2 continues. Okay, so I'd like to look at a problem in which, like 37, on page 290, we're given a bunch of information about a function. And they want us to create a graph. This is, again, all about the table. So I'm just going to copy. F prime of 0 is 0. F double prime of 0 is less than 0. F of 0 is 5. F prime of 2 is 0. F double prime of 2 is positive. F of 2 is 2. F prime of 4 is 0. F double prime of 4 is less than 0. And F of 4 is 3. If you ask me, what is this? I will say a mess. It's a mess. What is this? I have no idea. Once I put everything correctly in the table, the light will come on. Guaranteed. I need to summarize everything in the table. Piece by piece, step by step. Okay, so let's start. F of 0.
Can you please scoot the table up?
Yes, I think I should do this better.
There we go, that's perfect.
Is this better? I'm pushing my devices.
Yeah, oh, that's way.
Is this better? Okay, good.
Is that bottom one supposed to be
Of course.
F2
Of course.
prime or whatever?
Of course. Thank you. I owe you for keeping me on track. Thank you so much. Okay, now, piece by piece, I want to start with this. F of 0 is 5. This is done. I want to continue with F of 2 is 2. This is done. And F of 4 is 3. This is done. It found all, I found their spot in the table. Okay. Continue. F prime of 0 is 0. Okay. Which means that this is a critical number. So this is done. F prime of 2 is 0. Oh, another critical number. Okay, done. F prime of 4 is 0. Oops. Okay, another critical number. Awesome. So they all found their way in the table. So now let's see what this is all about. The second derivative at 0 is negative. Second derivative at 0 is negative, which means the function must be opening downward, which means 0, 5 is what type of point? 0, 5.
An IP.
Careful.
Is it IP?
When the second derivative is 0 or undefined. But it's not 0 or undefined, it's negative. So look at the shape.
Maximum?
Exactly. 0, 5 must be a relative max. So this found its way where it belongs. Done. The second derivative of 2 is positive. Second derivative at 2 is positive, which means at that point the function does this. Okay, so then what type of point is 2, 2 if the function must look like this? And this is a critical number, otherwise no, right? So these are critical numbers. The second derivative looks like is negative. So then the function looks like this. So then we identify that this particular critical number is a relative max. Now what about 2, 2? Knowing that the second derivative is positive, so then the shape has to be this. Yes. What is this?
Relative minimum.
It's a relative minimum indeed. So this found its way in the table. Done. The second derivative at 4 is negative. Second derivative at 4 is negative. Again, this says if the second derivative is negative, the function, we say, does not hold water. Here it does. Here it does not. This is a critical number in that area. In the vicinity of this point, this is how the function looks like, because the second derivative is negative. So 4, 3, what type of point would that be?
Maximum.
Yes.
Max.
Very good. That's it. So everything, all the information found its way correctly in the table. I don't need this anymore. I can come up with a graph. Looking at this, very doubtful that somebody can come up with a shape of a graph. There are multiple answers here. So we're just going to come up with one. You can come up with as many as you want. Okay, so here's the graph that I want to present. Of course, I have to have the point 0, 5. I have to have the point 2, 2. And I have to have the point 4, 3. In the middle, yes, I can put any IPs I want. I can do whatever I want. The rest is my choice. But I have to have what is given. The rest, I can do whatever I want. So at this point, there is a relative max. I'm going to say there is an inflection point here, because that's what I want. And then it changes concavity. It comes to a relative minimum. Goes back up. I'm just going to say it continues this way. And I should have an inflection point because I thought I could do it as a corner, but I can't do it because this is what I'm asked to do. So I have another inflection point here, and here it is. That's my graph. So opening downward, and it has a relative max at this point. Then it has an inflection point because it changes concavity, and it comes to a relative minimum, which is 2, 2. And then it gets to an inflection point again, changes concavity, comes to a maximum and goes down. So this is,
I have a quick question. I'm not understanding how you got the IP part of it, because on the graph it looks like at almost 1/4.
so
there's that.
so
that
I
dot,
can
but, like,
add anything I want. I can add an inflection point here, one here, anywhere I want. It's just that the function has to present what is given in the problem. Anything additional, it's my choice.
okay.
You can put a vertical asymptote here if that's what you want.
Okay.
You can put a vertical asymptote and then continue down this way and then come back up from the other side of the asymptote. It's up to you. I chose to use inflection points. So then the function works. I wanted to create a smooth continuous function, but you don't have to. You can put vertical asymptotes. You can do other things. This is just an example of how important this table is, where it tells you what to do and how to graph. Other questions for me? Anything? Anything? Okay, I'd like to look at a word problem so we can continue. Like 41, because I'll assign 42. So 41 on page 291. The gotta have it, I think, device is introduced in the market with 150 million potential buyers. Okay, the unit sales are modeled by the function S of X. Always take notes. Sales. Okay, negative 0.0131 x cubed plus 0.661 x squared minus. There are no two minuses. I'm just saying that this continues here. No, there are no two minuses, just one. Negative 2.021 x plus 6.865.